Hey there, in this video we're going to start covering chapter 9 and we're going to start with section 9.1, comparing two groups with a categorical response. So essentially we're going to be looking at comparing two proportions. Remember, when we have categorical response, that means our variable is categorical, so we look for then proportions because you have the categories, so you have choices for the responses, and so we can gather the proportion of percentage of people who answered a certain way. Versus quantitative, in quantitative data we're gathering numerical values and then we can find the average, a mean. But with categorical, we're looking at proportions. And so with categorical variables, we use the z-test, we use z-scores. With quantitative, that's when you have to really pay attention whether you're going to use z-scores or t-scores. And remember, that depends on whether you know the standard deviation of the population. If you know the standard deviation of the population, then you continue with the z-scores, so it will be a z-test. But if you don't know the standard deviation of a population, then you continue with the t-test. But back to this, we are dealing with a categorical variable, so we're looking at proportions. And what we have done in the past sections is just with one proportion or one mean. Now we have two groups. So let's see, the first thing that we're going to do is make sure that the samples are simple random samples, that the samples are independent. And just as a reminder, what does it mean to be independent? So samples are independent if the sample values selected from one population are not related to sample values from the other population. We got to make sure that we have at least 5 successes and 5 failures in each group. And so we'll talk about groups. Once you see an example, we're going to understand better what we mean by each group and why we might have two proportions. Our test statistic is P1 hat minus P2. So this is our from our sample. So the proportion from one sample, from one group, and then the proportion from the other group in the sample. The standardized statistic is our z-score. And remember, it's always the sample statistic minus the population parameter divided by the standard error. Oftentimes the standard deviation, or as we've been doing before, is the standard deviation over the square root of n, things like that. So here we have this kind of crazy looking formula, and notice that we have p hats there, p, so the p hat refers to the sample statistic. P with nothing on it refers to the population parameter. Notice that here you have a p bar. So what is p bar? P bar is what's called the weighted or pooled estimate of the population proportion. So let me add that in, or pooled estimate of the population proportions P1 and P2. And so let's look at our first example. The murderer's nurse. So this was a famous case in the 1990s. For several years in the 90s, Kristen Gilbert worked as a nurse in the intensive care unit of the Veterans Administration Hospital in Massachusetts. Over the course of her time there, other nurses came to suspect that she was killing patients by injecting them with the heart stimulant epinephrine, which is really adrenaline. Gilbert was eventually arrested and charged with these murders. Part of the evidence presented against this nurse at her murder trial was a statistical analysis conducted on 1,641 8-hour shifts during the time Gilbert worked in the ICU. For each of those shifts, researchers recorded two variables: whether or not she worked on the shift and whether or not at least one patient died during that shift or during the shift. So the first thing here is identify the observational units, right? Anytime you have a study, where or what or from who are you getting information from? So those are your observational units. And then we're going to classify the variable as categorical or quantitative. Now my hint here is that the observational units are not people. So what are the observational units? What are we looking at to get information? And hopefully you've seen that is the 1,641 8-hour shifts. So those are our observational units. Now, what are the variables? So once we're looking at the 1,641 8-hour shifts, what are we recording from that? And there are two variables. So we're looking at whether Gilbert worked on the shift, and then also whether or not at least one patient died during that shift. So those are our two variables. So let's say variable 1, and we can call it x1 if you want, is whether Gilbert was on the shift or not. So then this is categorical binary, because it's either yes or no. Variable 2 is whether a patient died on a shift or not. And so again, it's categorical and binary, because it's either yes, a patient died, or no, a patient did not die on that shift. So we have our observational units, which are the 8-hour shifts, and we have our variables, whether she worked or not and whether a patient died or not. Is this an observational study or an experiment? Explain how you know. If it is an experiment, identify the treatment group and the control group. So this is kind of going back to stuff that we did at the beginning of the semester. So what is an observational study versus what is an experiment? So the question, to see if it's an experiment, that means you have two groups, right? The treatment group and the control group. And that means that the researchers are actively engaging with the observational units and separating them. Here, there was none of that. It's just the shifts already happened, and we're just getting information from the shift that already happened. So nobody is putting, there's no control group putting her on a shift to see what happens and then putting a different nurse on a different shift to see what happens. So there was none of that. So we can say this is an observational study, because the researchers did not intervene with the shifts. So that can be our answer for that. And you can always write these answers in your own words, what makes sense to you, as long as you get the point across that the researchers were not intervening with how the shifts were happening. So plus what I already said, right? The shift already happened and we're just looking at it after the fact. So that is a good giveaway of an observational study. So what did the researchers find when they analyzed the 1,641 8-hour shifts? They found that Gilbert worked on 257 of the shift and she did not work on 1,384 of them. They also found that a patient died during 74 of the shifts and no death occurred on the other 1,567 shifts. So that's a lot of information right there. So explain why the information in the previous paragraph does not provide any clues about whether there is an association between Gilbert working on a shift and a patient dying during the shift. What additional information do you need to know? So let's look at the information given again. So of all the shifts, it was found that she worked on 257 of the shifts. And they also found that a patient died during 74 of the shifts. So they're talking here about the 1,641. So what would be more helpful would be if we knew of the people who died, right, on those 74 shifts, how many were shifts that Gilbert was working on. So we will need that piece of information. So here's some additional information now. Among the 74 shifts during which a patient died, 40 were shifts on which she was working and 34 were shifts when she did not work. So here, let's explain now why simply comparing only the numbers 40 and 34 is not very informative. Because from the looks of them, 40 and 34, they're not very far apart. So why are they not that informative? What else would we need? What would we rather look at? So the counts alone are not helpful. We can say we need to know the proportions of death, the percentages of deaths that occur. Right? Knowing the percentage, the proportion might be better than just knowing the counts. 40 and 34 seem pretty close, but we are talking about very different numbers. 1,641 is the total number of shifts. So, and we have other numbers here. So we need to really get the proportion. What does 40 mean? 40 out of what? And then the 34 is 34 out of what? So that's what we need. We need proportions to make better comparisons. So let's organize our data into a 2x2 table of counts so that we can then get the proportion. So let's see, what do we know? Patient died during the shift and Gilbert was working on it. Do we know how many of those happened? Yeah, we know that 40 were shifts on which Gilbert worked and then 34 shifts she did not work when a patient died, right? Among the 74 shifts during which a patient died, 40 is when she was working. So that means that this number will be 40, which then means that this will be 34 because they have to add up to 74. Plus it also tells us 40 were shift on which she was working, and then the other 34 she wasn't working. So a patient died, 40 died when she was working and 34 when she was not working. And now we can do some math to just find the missing values here. So 257, this has to add up to 257. So then that means that the number here is 257 minus 40, which is 217. And here 1384 is the total. So the missing number then is the 1384 minus 34, which will be 1350. So now let's gather the proportions. So just a better way to compare the outcomes, we want to compare then the proportions of death, or the death rates on the shifts. So this will be a better way. Compare the death rate when Gilbert was working to the death rate when she was not working. And so now let's go and find those proportions. So calculate the conditional proportion of Gilbert shifts on which a patient died. So my hint is to put the total number of Gilbert shifts in the denominator of your fraction. And we're going to call this P1 hat. So this is our sample statistic for the first variable. So to find the proportion when she was working, so we know that 40 people died while she was working, but the total number of shifts that she worked was 257. So it will be 40 out of 257 will be the Gilbert shifts. So that will be here, 40 out of 257. Put that on our calculator and we get 0.156. Now what about the conditional proportion of non-Gilbert shifts? So that will be when she was not working, 34 people died out of how many? 34 out of 1384. So that will be our P2 proportion. So that gives us our P2 hat, right? Sample proportion, 34 people died out of a total of 1384, the shift where she was not working, which gives us 0.025. Now look at the proportions. So if you convert this to a percent, so what can you say? This is approximately 15.6%, which is almost 16%. And then what about this one? This is 2.5%. And now look at the difference, right? When we were looking first at just the numbers, 40 and 34, they seem pretty close. 40 and 34, 6 people, right? But when you look at the proportions or the percentages, that's almost 16% and that's 2.5%. That's a big difference. So just with these, do we have an idea that she was involved in these deaths? What do you think? Right? The shift that she wasn't working, 2.5 is the percentage of death rate versus the shift that she was working, almost 16%. So that's a big difference. You can even probably do a ratio to see how much bigger the 15.6% is than the 2.5. It's like a little over 3 times bigger, right? So okay, so now let's go calculate the difference in conditional proportions of death between Gilbert shifts and non-Gilbert shifts. And why do we want the difference? Going back to when we do a z-test for the difference in proportions, our statistic is the P1 hat minus P2 hat. So it's the difference in our sample proportions. So that's why we need the difference. So let's find the difference between our P1 hat and P2 hat. Computing the difference, we get 0.131. So you want to do the P1 hat, so the 0.156 minus the P2 hat, which is 0.025. Leave them in the proportion form, not the percentage. I just did the percentages to compare them because sometimes it's easier to look at them as whole percentages than as the decimals. All right, so then this is our sample statistic, the 0.131. That's our what we're going to use to do our two-sample Z-test. So we want to test the claim that Gilbert was responsible for the death on her shift at the Veterans Administration Hospital, and we're going to use a 0.05 significance level and the p-value method. So I'm also gonna show you how to do the confidence interval method, although the p-value method is the one that is universally most used, and that's because the confidence interval, well, I'll talk about it when we get to the confidence interval, but for the confidence interval, we're strictly using the data from the sample, and so it gives a little more room for error in hypothesis testing versus when we do a hypothesis, we do a hypothesis assuming that the null hypothesis is true, and the null hypothesis is about the population parameter. So that already makes it more precise because we're assuming something about the population, whereas a confidence interval, everything is coming from the sample. All right, so our steps to follow are pretty similar to what we did before with the hypothesis test for a single proportion and for a single mean. We're still going to verify that the samples are simple random and that they're independent. We still need to verify that that our sample meets the criteria of the central limit theorem. So in this case, is that the number of successes and failures in each group is at least 5. And the level of significance we know is given to us as 0.05. Almost always you're going to be given the level of significance. The only time you're not going to have it is if you are creating your own study, and so then you need to provide the level of significance that you want. And remember, the level of significance is the maximum allowed probability of getting a type 1 error. So a type 1 error is rejecting the null hypothesis when the null hypothesis is in fact true. So we want that error to be very minimal, very small. And so that's why 0.05 is the maximum allowable probability of getting that error. And then we want to state our hypotheses. So identify the null and the alternate hypotheses. And because notice that our standardized statistic to find our z-score, we need the pooled estimate of P1 and P2, then that's going to be our first step, is finding that p-bar. And then we're going to find our standardized statistic. Once we have the z-score, we're going to find the corresponding p-value. And then once we have the p-value, we're going to make a decision. Are we going to reject the null or fail to reject the null? And then we're going to interpret our decision in the context of the original claim. All right, so let's follow those steps for this particular study. So first, in verifying that the samples are random and independent, we can say that they are because the shifts are random shifts from the hospital database during the time that Gilbert worked there. Now let's verify that the number of successes and failures in each group are at least 5. And so this is where the table comes in pretty handy, because when we look at the table, we can see right away the numbers. So there were 40 successes. Well, success in this case is that this happened. 40 people died when she was working. So that is a success in the context of our study. And then failure will be 34, and then the other one, success, is 217 and failure is 1350. So these are everything is more than 5. So that condition is met, so that means we can use the central limit theorem so we can find our test statistic. So we can say all successes and failures are more than 5. Specify the level of significance. This was given to us to be alpha was 0.05. And now we're going to state the claim mathematically and verbally. Verbally just helps you to think about what the problem is or what the study is, so that then later when we're going to interpret it in the context of the problem, we have an idea already because we already have the hypothesis written in words. So this means identify the null and alternative. So let's see. So what is it? What is the claim? So the claim is that Gilbert is responsible, right? This says right here, Gilbert was responsible for the death on her shift at the Veterans Administration Hospital. So if she's responsible, what do you expect the difference to be, right? So if she's responsible for the death, that means that we expect her proportion, the proportion of death while she was working, to be greater than. So we then in all of the shifts, we expect then P1 to be greater than P2. So that's going to be, but then greater than, that doesn't have an equality statement, so that must be the alternative hypothesis, which means that the null hypothesis is, let me change the color of that. So then the null hypothesis will be, we have to include here the equality statement. So that means that there's no difference, right? That her proportion of deaths will be the same as the proportion of death when she wasn't working. So meaning that there's no difference between P1 and P2. So what we can say then is that there's no difference between the death rates when Gilbert was working versus when she wasn't working. So we can say that in words, and then in symbols, it will be, what does it mean to say there is no difference? That means then that the difference is 0. So here we can say, so H null is P1 minus P2 is equal to 0. So this is our null hypothesis. So what about the alternative hypothesis? We already talked about the alternative, that then the proportion of deaths on her shifts is larger. So we can say the death rate on Gilbert's shifts is larger. And how do we say that mathematically? So this is where we bring in the greater than. And so now we can see, okay, the null hypothesis has the equality statement. Remember, the alternative always has either greater than, less than, or not equals, while the null always has some sort of equals, right? The equals, greater than or equal to, or less than or equal to. Now you might be wondering, why are we doing P1 minus P2? Another way to say the null hypothesis would be that the death rates are the same. But if you say that the death rates are the same, then what are you really saying? When we say that the death rates are the same, what we will be saying is that P1 minus P1 is equal to P2, sorry. And then when you subtract P2 from both sides, you get P1 minus P2 equals 0. So saying that the death rates are the same, it essentially means that there's no difference. So because we want to look at the difference on them, that's why we kind of go straight to that. So we'll be doing that also as we study two means. We'll be looking at the difference between the two. If the difference is 0, that means they're the same. If the difference is not 0, that means one of them is larger. Right, so if the difference is positive, that means P1 is larger. If the difference is negative, that means P2 is larger, and so on. So now that we have our hypotheses, let's pay attention to the alternative, because the alternative is what tells us what kind of test we have. Since we have a greater than symbol, what does this tell us? What kind of test do we have? Left tail, right tail, or two tail? And yeah, this will be a right-tailed test, meaning that when you look at the p-value, pretend that that's symmetric and normal, then we're looking at this. So whenever we find our z-score, we want that area. So this is going to be our p-value. Now remember, our z-score table in our book gives us the area to the left. So that's why, because this is a right-tailed test, then our probability here, our p-value, is going to be 1 minus whatever we get for our z-score, which is going to come from step 6. All right, so let's go, and we need to find our standardized statistic, or z-score, but in order to do that, we need this step first. We want to find the pool estimate for P1 and P2. So let's define a little bit here what things are. So x1 and x2 are the numbers on each of the shifts. So x1 is essentially the number of deaths while Gilbert was working. And then x2 is the number of deaths while she wasn't working. And 1 is the total number of shifts where she was working. So number of shifts that she worked. And then N2 then is the number of shifts that she did not work. So number of shifts she, let's say, did not work. All right, so that means then our P bar is going to be the number of deaths while she worked, that was 40, and the number of deaths while she did not work, that was 34, divided by her number of shifts, that was 257, and the number of shifts she did not work, what was that number? Let me go back to our notes. We had it right here. So her shifts were 257. The shifts she did not work were 1384. So 1384. And so when we put that, so it ends up being essentially the total number of deaths, which is 74, divided by the total number of shifts, which we already know is the 1641. And when we put that in our calculator, we get 0.0451. So this is our P bar. What about, so this is our pool estimate of P1 and P2. And P1 and P2, remember, those are population parameters. This is what, so we could do a confidence interval to see what is the true proportion of deaths on shift when she was working, right, on all of her shifts. So let's try, what about Q bar? Well, Q bar is 1 minus P bar. So this will be 1 minus 0.0451, which we get 0.9549. So that's our P bar and Q bar. And we need those so that we can compute our standardized statistic, so our z-score. So now we're ready to compute this. So let me give myself more room here. All right, so now we're ready to compute our standardized statistics. So we can say then z is going to be equal to our P1 hat minus P2 hat. So this is our sample proportions for each death rate when she was working versus when she was not working. And we had already computed that in number 8. So this was 0.131. So let's go back to our notes. So that is the difference from our sample is 0.131 minus our population parameter, P1 minus P2. And this comes from our hypotheses. We're claiming, remember when we do hypothesis tests, we assume that the null is true. So we're always kind of testing the null, whether the null is true or not. So P1 minus P2 we're saying is 0. There's no difference. So that means our P1 minus P2 here will be 0 for the population. So this comes from our hypotheses. Usually the null. Divided by P bar, Q bar, so those are the ones we just found. So the square root of 0.0451, that's P bar times Q bar, which we found it to be 0.9549, and then times the quantity 1 over N1, so 1 over 257 plus 1 over N2, 1384. Now be careful here. Algebraically, you don't want to make the mistake of saying like, oh, let me add these up and it's 1 over 1641. That is not true. These are not common denominators, so you can't combine these fractions. In order to combine them, you will have to first get a common denominator. But we can just input this entire thing onto our calculators. Be very careful to use parentheses. So what I will do, or what I did, is do 0.131 and then just leave that. Do this whole calculation and get what this is with the square root, and then do 0.31 divided by my answer. And then that's how I get my test statistic, my standardized statistic, which is 9.29. So play around with your calculator and make sure that you do get this answer so that then you know how to use your calculator correctly, or you know that you're using it correctly. Now that we have our z-score, we go and find the corresponding p-value or the critical region. Now remember, we do have a right tail test, and that comes from, ooh, that one was way better. That comes from the alternative. So essentially, I'm going to have 9.29. So I want to figure out what is the area over that, right above 9.29. So this is a huge z-score. So even if we just were doing the empirical rule, what did the empirical rule tell us? That any values that were more than 2 were highly significant, right? Highly unlikely. And more than 3.5 is they're even more unlikely to happen. So this is 9.29. So just even based on the empirical rule, I can tell that this is not going to be good for the null hypothesis. Like, we're probably going to reject it because this z-score is so high, so far away from the mean. So let's look at the table. Since it's a positive z-score, I'm going to look at the positive table, and notice that 9.29 is not even in here. It goes to 3.50 and up. So this is 0.999, but remember, this is giving me the area to the left. So my area then is 1 minus this 0.999. So when I go find my p-value is, right, is the probability that z is greater than 9.29. Now that I have my standardized statistic, but because the table gives me the area to the left, then I have to say this is 1 minus the probability that z is less than 9.29, which I found it to be 0.999. So my p-value ends up being 0.0001. Make a decision to reject or fail to reject the null hypothesis. So this is where what do? We compare our p-value to our alpha and then see which one is smaller. So our p-value is 0.0001 and our alpha is 0.05. So what can we say? Our p-value is smaller, so that means we reject the null. So rejecting the null, what does that mean? Let's go back and look at the null. The null says that there's no difference between death rates. So rejecting the null is saying, like, there's sufficient evidence to reject this claim. So what is happening is then is more likely that the alternative is plausible. So we can say we have strong evidence to suggest that the death rate on Gilbert's shifts is in fact larger. So that's what it means to reject the null. Interpret the decision in the context of the problem. We kind of already did that by just saying what it means to reject the null hypothesis. So let me write that down. So we can say because we reject a null, this means we have sufficient evidence to consider the claim that Gilbert's shifts had a higher death rate. So that's what it means to write it in the context of the original claim. So hopefully this is making sense. So it's very similar to when we did it with the proportions and with the means. It's just that now there's that added element of our z-score just became more complicated, right? The formula looks a little crazier. So make sure that you have this in a 3x5 note card, or if you have a 3 or 8.5 by 11 piece of paper with your notes or formulas to know for quizzes and tests, make sure that you start adding this one in there with also the P bar, the pool estimate, and for P, and the pool estimate for Q is just 1 minus P bar. All right, so then this kind of finishes up our claim or our hypothesis testing for this particular problem. So let's go back to the notes and finish up the rest of the questions. So now that we have shown that we have convincing evidence, or our statistical analysis, right, showed us evidence that the death rates for Gilbert's is potentially higher, this part is asking, is this convincing evidence that Gilbert caused the higher probability of death in her shifts? Explain as if you are her attorney. So if you were the defense attorney, could you say then, is this convincing evidence that Gilbert caused the higher probability of deaths in her shift? And so think about that, and what are some reasons that you could give that to poke holes at the hypothesis test? Some of the ideas that came up for me are, no, right, we have to consider other nurses who work the same shift, and we need more data on the shifts. So number 11, and email me any of the other reasons that you have, or maybe will this be a good thing to put as a discussion? What are some of the other things that people come up with, and maybe share them out. Number 11, is it reasonable to conclude from this analysis that Kristen Gilbert was responsible for the increased chance of death on her shifts, or that she caused the deaths on her shifts? Explain your answer. So, and remember what kind of study this is. This is an observational study, so how does that change things for you as you think about them? So we can't necessarily conclude that she caused the death, but we can say that there's enough evidence to look into the case further, since the death rate on her shifts was so much higher. Now, I want you to suggest an alternative explanation that the defense attorney might use to explain the large difference in death proportions between the two groups. So what could be some reasons that the rate of death is higher during her shifts than any other shifts? So think about what could be going on, and that is not necessarily just because she was killing people. Like, as the defense attorney, the idea is you want to poke holes at what the prosecution is suggesting, right? And in this case, poking holes at the statistical analysis we have done. So what are some other explanations? And so this is where kind of like co-founding variables come in. Sure, the rate is higher, but what else could be causing those deaths that is not necessarily she's killing them? So think about, where does she work, right? This was a veterans hospital. In what department did she work? She worked in the ICU, intensive care unit. So what are some things that you could then bring up to say it's not her that was killing the patients? It's what are some other variables that could be going on? So think about that. I will create a discussion and have you guys put in your input for these, for number 10 and number 12 in that discussion. All right, so in the next video, I'll do the confidence interval estimate for this same problem using StatCrunch, and then I'll do my math lab example.